Hello, everyone. Welcome to our last session for the Daily Study Group series, Introduction to Machine Learning. We've covered chapters 1, 2, 3, 4, and 6. We left out chapter 5, and we were hoping to at least look at it briefly today. Turns out it is a pretty deep and a pretty long chapter. There's a lot of material covered here, and I'm not sure if I'll be able to do justice to properly covering all the material in here. However, if you have been able to read through the chapter, you have specific questions, please go ahead and put them in the Q&A pane. We'll be happy to look at those questions. I have Luke Titus here with me, my colleague from Wolfram Technology Group. Luke has done a fantastic job of answering all your questions throughout the week. We couldn't have done this study group without his help. And we will have the first few minutes open for some basic questions I had, just your general experience with the study group, the kind of paradigms and models and approaches you've been learning about. You've seen some examples of using machine learning in Wolfram Language, using different kinds of data. So I was generally curious about what you found interesting, what you might be working on. And while I push out those poll questions, once you've answered them, feel free to put in questions in the Q&A pane about this specific chapter. I have also collected some questions from the surveys feedback that we have received. Usually there is this question like, what's on your mind, what you want to review. So we will start out by reviewing those questions that I have collected over the week. And then towards the end of the session, we will look at some a brief collection of points from this chapter 5, how it works, that I thought might be useful as a nice summary of our entire series, some useful takeaways from this introduction to machine learning. So, all right. As we start off, my first question, I was really curious about this, and the Introduction to Machine Learning book has been out for quite some time. I was curious, before coming to this study group series, were you aware of this book, aware of this resource, the fact that it is free, it's online, all the code is available for you to download and try and learn from. And the fantastic resource, really. It strikes this amazing balance between going into the depth of certain topics, but overall giving us hands-on examples that even if you were not interested in diving into the theory of things, you just wanted to start off right away with code, start off right away by trying to apply some of these algorithms that have already been efficiently implemented in Wolfram Language, sort of off-the-shelf machine learning. There were tons of examples in the book about that as well. So 60% of our attendees did not know about the book. I'm so glad that we were able to do this study group, and I hope it has sparked your interest. I know by no means we've covered everything in details, even in the first 6 chapters, but I do hope this has been a good launching point and you'll be able to read more of it. At least we gave you some pointers, some help in getting started, how to work with the code. Yes, there are issues. I acknowledge we ran into some issues with the code, but I do hope for the majority of the examples, you'll be able to run the code in the notebooks version that you have downloaded, and will be able to work on it further. Okay, so we covered classification, regression, and clustering. I was curious, from what you've seen so far, what type of machine learning paradigm are you most likely to use going forward? Whether you have a project in mind, maybe you have a data set that you've been looking at work, or for research, did you find a paradigm, an approach that would work for your data set? Or maybe you came in just to learn about machine learning. Did one of the machine learning paradigms appeal to you, and probably you're looking for some example data sets that you might be able to work with? So for the beginners who just got introduced to machine learning and are looking for data sets to work on, one great resource is the Wolfram Data Repository. And you can see you can either browse datasets by categories, topic areas, and then even in the topic areas, there are things like earth science, demographics, government data, just images and all of this. And then there's this entire category of machine learning. And you will see here some of the example datasets that we've been working with, but a whole bunch of other datasets as well. And then if you're interested in looking like, what type of data you want to work with, image, numeric data, audio, text, and so on, you have these here as well. In addition, two useful sources I have found is one is the UCI machine learning repository. And if you just Google it, you'll have a whole bunch of popular data sets and even some new data sets here. This is a great resource for someone starting out, trying to look for data sets, easy data sets to work with, because if you right away off the bat you go out and get data from the wild, it can be a little frustrating because you'll end up spending 90% of your time just struggling with the data, cleaning it, wrangling it, and you won't really be able to get to the interesting machine learning part of the workflow. So if you want to work with data sets like these hello world data sets that people have worked on classically as they have started machine learning, this is another good place to look. And then a third resource is this community here. They have a very nice collection of data sets, and they often have these competitions that they test people on how well their models perform. But if you go to data sets, you can browse through their data sets as well. All right, so see, a lot of interest in supervised learning regression, closely followed by classification and clustering. And then some folks are interested in other types of machine learning that we did not cover in the study group. If you wouldn't mind sharing, we'd love to see if you would like to put in the Q&A pane what type of machine learning you're interested in beyond classification, regression, and clustering. I'd love to see that. And then finally, what type of data do you have that you're going to work with? Is it primarily numeric data, textual data, images? In the feedback, I saw a couple of mentions of image data that some folks are planning to work with. Just curious if anyone has any thoughts about working with audio, video data, or what is more common in real life, really mixed types of data. Your data set contains both, and not just numeric and text, but collection of different types of features, different types of attributes. Nice. Mostly numeric data, mixed types of data. So some folks are definitely going to work with audio and video data, and then a good mix of text and images. Thank you for sharing that. We definitely appreciate your joining this study group, actively participating in it. Okay, so let's start off with the review first, and then we can go on to this other, the second half of the session, and reviewing that chapter 5, how it works. So firstly, I acknowledge that we ran into issues with errors in the code. Thank you for your patience. I did post some of the corrections that I got to, I posted on community. So if you we posted the link to community on the chat pane, so you can go over and you can see some folks had posted the issues they were having, and then I tried to clean up and debug some of the code. I will definitely be forwarding those issues to our publishing team, so hopefully we can get that fixed in the next version of the book. Okay. Right off the bat, let's look at some very basic questions and some very good questions. Um, Formatting the data, right? We've been using a few different ways, but that's like one of the most important things as we get ready to use machine learning with Wolfram language, right? So let's quickly go over a few different ways in which you can provide data to the classify function. So remember, classify is for classification, which is supervised machine learning, which means there has to be some labels attached to each data sample, right? Either we are going to classify emails as spam or not spam, in which case every email text should have an associated label like spam or not spam. So it is has to be an example and its associated label. So in what you're seeing on my screen right now, the example stands for the data point and class stands for the label. It could be class A or class B, class A, B, C, D, E, whatever. So we have to provide that association in certain way. We can do it in these ways. We can attach each label to its associated example, and then we make a list of all these. So we have example 1, class 1, example 2, class 2. We worked with the iris dataset, remember yesterday? So there we had examples from different species of the iris flower, and the features were these lengths, the petal width, sepal width, they were numbers. So this list here represents that sample, maybe petal length, petal width, sepal width, and I don't exactly remember the order, but this is the associated class, and so we have the label in here. So I could represent my data in this way, right? The entire example and its associated label. It could get a little cumbersome if the way I have imported my data. It isn't that difficult. You would need some Wolfram language code. You would need things like the map function, the part function, and you can massage the data and get it into this format. However, in some cases it might just be easy to get a list of all the classes and a list of all the examples. However, in this case, you have to ensure that the ordering is the same in both cases. So you have list of all the examples in here, and you must have the class labels in that exact same order here. And then you can, just say, oh, all these examples and point them to all these class labels. So the same, oh, I wish I had created the example with the same data, but here, for example, if you were to do image classification, images of handwritten digits, so I have all the samples in here. Okay, all images of all the samples. I have images of all the other samples in here. Um, and so they are grouped by the classes, right? So I can say, oh, this whole list, this is class 0. This whole list, this is class 1. This whole list, this is class 2. And this whole list, this is class 9. What is a little more intuitive is grouping the samples by classes in an association. So here I have examples of all the images that belong to the class Griffin, or examples of all the images that belong to the class Centaur. And I've put this in an association. Notice the different set of characters here, especially beginners. This is different from a list, but the classify function is able to handle it just fine. Um, is there a preference to use one over the other? Not really. You can use whatever works for you. Sometimes I feel this is really just the easiest way to interpret the data. I can see, oh, these are my features and this is my class label. So I think you can't go wrong with whichever way you use. And then the fourth option that I don't have here, but you do see used in the textbook is the data set, where you have the data set and you just say the label is the column name and it is able to pick that up. Okay, so one of the questions from yesterday was definitely how and why behind what to do. That is what really this chapter discusses. But I want to mention that your friends for getting into the how and why and what is happening in a model are these functions: the information function, the classifier measurements function, and the predictor measurements function. With the information function, and we'll see this in the examples coming up, as soon as you've built your model, you can use information and you can extract a lot of information about the model itself. So this is a good way to explore and learn more about what is happening. And then if you have a test data set, which is a requirement because you don't just build the model, you try to evaluate the performance of the model. You have the classifier measurements and the predictor measurements function. This is of course with supervised learning. You use those functions to learn more about how your model performed in on the test set. So these are the three main functions you would end up using to learn more about what is going on, and they can also be used as tools to learn how the model changes based on tweaks that you're making, either to the parameters, hyperparameters, the data, how you slice and dice the data, how you augment the data. So every time you run it, you can check with these functions how your model has performed. So one of the things somebody had asked about is more about the learning curve. So this is an option for information. So when we run classify, you can see briefly when the training progress indicator flashes. Actually, we can try and run that and see if we'll be looking if the training progress indicator will appear. Uh, Oh, that was very brief because I have such a small data set right here. But anyway, you can see that the training is progressing. And if in a case like this, where the training is really quick and you haven't had a chance to see what's going on, you can look for more information on your model. So just asking for information gives you this neat and tidy report and gives you some basic information of the data type, the classes, accuracy, the method that was used, and some information about how the training process progressed. But if you are interested in more details, like many other Wolfram language function, you want to put in properties and you say, okay, give me all the properties I can look for this model. And here you see you have a nice list of properties. And there, if you were interested in the learning curve, it's right here. And you can just pull out the learning curve and you can see the learning curve shows you how when you added more examples, how the learning improved. Okay, and you can see here exactly as you added more training examples, the accuracy really took off. So it was somewhere here. And the model was using, I think it's using logistic regression, and it was using an L2 regularization of 0.1. But then here, it with more examples, it ended up using an L2 regularization value of 0.1, and the accuracy improved. Not a huge amount, but it went from, I think, about, what do you say, 0.775 to almost 0.9 here. So you can pull out the learning curve and look at it in this way using information. Now, beyond learning curve, there are other performance measures you can look at, and there were some questions about, statistical measure, about how sensitive the regression model is, or some of the measures that we talked about in the regression lesson: residuals, mean square error, root mean square error, comparison plot. So of course, the best place to look for all this information is predictor measurements in case of regression, or classifier measurements in case of classification. And so here are the details, and you can see all sorts of measures that you can obtain from the measurements object. It's pretty detailed, lots and lots of things you can just dig into and ask the predictor measurement objects to give, to provide. And so again, let's do an example here. We'll work with the Boston Holmes dataset, and you'll notice I'm pulling it in from example data this time instead of the data resource. And you will notice that even if you don't have internet connection, this set of da- data is actually built into the language. If you're working offline on your system in Mathematica, you will have this collection of data sets built in that you can pull in, and you will see there's a machine learning category, so you can just pull in data sets from this category and just work with it. So I'm pulling in the Boston Homes data sets, the identical data set to what is used in the book, and I have the option of just pulling in the training data or the test data. I decided to just pull in the training data, and then just create a predictor on it. And you can see here, as the training progressed, it was trying to show me what was happening. But beyond that, I can, instead of information, this time I'm using predictor measurements. And if you're trying to use predictor measurements, of course, one important thing is you need test data. How will you measure the performance if you cannot test your model on some new data? And ideally, this should be completely different from your training data. This should be data that the model has never seen before. So with example data, I can just pull in test data separately. And now here I can see all these performance measures. I can see, the standard deviation, the root mean squared error, cross entropy, and then I can see the comparison plot. The comparison plot shows you the predicted values against the actual values. So it nicely follows the line of perfect prediction, and it shows you how well my model has performed. And then again, if you just want specific details, you can look for properties with predictor measurements, and you can see all these different types of information is available. So if you're interested in just the residual plot, you can see the residuals of the prices. So these are the predicted values, and the residual being the actual value minus the predicted value. And you can see we was really off here in this case. A whole bunch of cases where the prediction was pretty close to the actual value. You can create a histogram out of that. You can just pull out the standard deviation and the standard deviation with uncertainty. So it's a nice highlight of how the automated machine learning framework makes it much easier for applying machine learning to your problem. If you were going to be lost in writing code to create a histogram out of the residuals instead of actually focusing on what information you can glean from the residual histogram, that would be a waste of your time. So that's where the automated machine learning framework in Wolfram Language comes in really, really handy. Okay. So now that we can assess the performance of the model, that makes it really easy to compare models. So there were some questions about, I think there was one question about getting some example data in the form like this. And you can see it's exactly in the form that we saw in the second option here. We saw it for classification, but it works just great for regression as well, because in regression, the label is just numeric. That's really the difference with classification. So now, yeah, sure, you can have your data in that form, and I have it here. You see, this is my uh, data set. It has only one feature. Okay, so just one numeric attribute, and this is the predictor variable, the dependent variable that I'm trying to predict with regression. So for 1, the value is 2, for 2, it's 3, for 3, it's 5, and so on. Now suppose, as the question stated, that you wanted to decide what type of method you wanted to use based on the data. One approach would be to get your data in, right? And then try predict with one method, have it trained, then try predict with another method. And you could use predictor measurements to compare the performance on some test data. Or in this case, this being just such a simple model, I can go ahead and just plot and see how the prediction changes. So these are the numeric attributes, and this is the predicted variable. And you can see that with linear regression, of course, I have this nice straight line, but for nearest neighbor, I have this interesting prediction curve, like, while my input values are 1 and 2, it sticks to 2, and then once I've y- once it right up to 2, it sticks to the prediction of 2, and then once 2 it goes off to 4, and it has, it's a much more interesting nature than the straight line from linear regression. Okay, now while working with linear regression and predict, there was a very valid question about regularization, and in the textbook here, Etienne does spend an entire section on regularization. I have to admit it's not my strongest point, so I'm not going to try to get into it and try to explain. Or what I can tell you is, if you're looking from application side of things, you can think of regularization as a way to limit the model from overfitting, right? You want to keep your model as generalized as possible, and you do not want it to be so closely fitted to your input training data that anything other than the input training data it deems as it's not, it doesn't know what to do with it and gives you wild results. So regularization, as the term suggests, is kind of limiting the performance of the model in a certain way. And while Etienne talks in details about regularization here in this section, um, I found another nice resource that I can share with you. I will be sharing this notebook with you, so don't worry about all the links I've been sharing. We'll put it in the same download folder, and we'll send out the link to you in the recording reminder email. And you can maybe this resource might be helpful in understanding a little more about regularization, especially in the context of linear regression. We also have a section of our documentation that is devoted to regularization in the context of neural networks. In this study group, we haven't really touched neural networks, but I have some resources later on. There were a few questions about neural networks. There are some examples using neural networks. So that would be another resource for understanding regularization, however, only in the context of neural networks. There was a question about managing models over time. So I'm not quite sure what that was referring to. I interpreted it as like, oh, I have trained a model. Now, if I quit my Mathematica session, is that it? I lose my model? And then if I have to use it again, what do I do? So in Wolfram language, if you are building models with at least classify or predict, then you can save the model in the Wolfram language machine learning format. So for example, here's a really, really simple model I'm going to build, and then I can export it as in this particular in this particular format. And then now if I quit my session, of course, if I try to use C 2.5, oops, okay, let's try that again. It doesn't know what to do, but I can always go ahead. See, I don't know where my model is right now. I better get it back. I hope it is in this directory. I've gotten my model back, and okay, maybe I need to name it. I thought I could use it right away. So yeah, I can import my model back, name it same or something else, and I can continue to use it. So this is also a way, if you are going to deploy something to the cloud, for example, you could create your model and have that model deployed to the cloud, and then separately you can make your form, and then you deploy the form function to the cloud, and you can internally call that model from within your cloud directory. Okay, let's take a brief look at neural net. It didn't seem fair to complete an entire study group on introduction to machine learning and then not do anything with neural net. So we'll do this really simple, the brain and body weight example from the regression chapter. But if you're really interested in neural net, firstly, we have an excellent hands-on tutorial written by one of the original developers of the entire neural network framework in Wolfram Language. Very hands-on, very detailed. I would highly recommend it. It's in the documentation. If you just search for neural networks, that'll be one of the links you'll get. And then additionally, we have also recently started the Wolfram U course, Introduction to Neural Networks. I think there's one scheduled for July 18th if you're interested. We offer this in regular rotation. It again does not go into details, but provides a nice overview of the neural net framework and what you can do and get you introduced to neural networks in Wolfram Language. So let's try this example again. I've been using example data here, for example, and you know, a lot of statistics data set can easily be used for machine learning, at least when you're exploring and learning things. So if you look up all the entire statistics data set, you'll see there is the animal weights data set, and it tells you it has the brain and body weights for 28 animal species. So I can just get that data set. I can see I have brain and body weights from everything ranging from a mountain beaver to a brachiosaurus. And it's really the same data set from the resource data from the data repository, which comes in this nice formatted data set. And if I were to run the code that's in the lesson, in the textbook, I think I just copy pasted it here. I just made the list plot a little simpler, but I did have to include plot range full because of this outlier here, which was giving me grief. But now if I just have a scatter plot of brain and body weights of these animals, I can see it's kind of you know, clustered here, and then there are a couple of outliers, this one in particular, the brachiosaurus, right here, with a really high body weight compared to a really low brain weight. So this spread is the reason Etienne recommends a log transformation of the data. So if we were just to create a list log plot of the data, then we see we have a nicer scatter plot of the data that we can actually work with. So log transformation makes it good for predictions for most models, because they can have trouble handling the data when it spans several orders of magnitude. So this would be one of the easy data pre-processing steps that you could take if you had similar numeric data. So we create a log of all the body and the brain weights, and these are the values now we have. And now we can train a neural net. We have a really simple neural network here. So neural networks is really just a collection of very basic computational operations, really multiplication and addition. So we are going to create a net chain of a linear layer that really just does the linear operation, multiplies each of the inputs. In this case, we have two inputs, so it will multiply each of the inputs here with a weight. So it will have, this layer has 3 nodes. Each node has two weights. And so the input is multiplied by the weights, and then you add a bias value to that and add it all up, and then you send the output from the linear layer onto the next layer. So I have 3 nodes in my linear layer. If you ask me, why did he choose to put 3 nodes in the linear layer? Why is it of a size 3? I don't have an answer for you. In most cases, I've seen the model of the network that you create does not really um, is not really created from some fundamental idea about how this model should look like, how this model can actually work with input data. It's very, I think, and as Stephen Wolfram said in his blog post, what is ChatGPT and how is it working, which really is a great introduction to neural networks for all beginners, that it was a piece of engineering that seemed to work and was therefore used. So in this case, for a simple regression problem, this sort of an architecture having a 3-node linear layer, then a tanh layer which applies the tanh function to each output of the linear layer, having a 2-node linear layer, again having a tanh, again having a 1-node linear layer that ultimately gives you one value as output. This sort of an architecture just seemed to work. And so we have it here. So we'll go ahead and put that architecture together, and you will notice when you use the neural net framework and a container like NetChain, which is just a way of putting the layers together, you will see that, you know, if you put it together, there's this red warning saying it's uninitialized. So all the parameters of the neural network, the weights and biases, they have been randomly assigned. It's kind of like an untuned piano. You have the the string attached correctly to the keys, but it has not been tuned. The tension has not been fixed, so that when the hammer hits the string, you'll get all sorts of notes that you will not quite associate it with that particular key. So that's why we have the warning here. The parameter values have to be adjusted, and the way you do that is by training the network. You show it these values and the training data, and then based on the training data, the network tries to adjust the weights and biases of the parameters in there, and it tunes the piano. So ultimately, when you hit the key, you get the right note. So when you provide an input, you get a plausible output. When you have built a network, again, you can use the information function. It's kind of generalized across many Wolfram language models. So it will give you more details about the network that you have built. Here is an example of just training the data. It takes longer time. It's much more detailed. The training progress indicator, it's even interactive. You can stop it and return just the partial result. What it is doing is taking batches of the data. It's such a small data set, right? So it tries to take a few of these samples at a time, builds a model, tweaks the parameters, and then tries to return the output and checks the loss function for each sample and sees how badly the network is performing, and then tweaks the parameter values. And there are well-established algorithms for doing that. If you're just wanting to use the neural net model, you don't have to worry so much about those. But then once we have the trained model, here Etienne creates a really simple example because we applied the log function to the input. We need to do the inverse operation, exponentiation, to get the output back. So if you have an input, you're going to create the log of it, feed it into our model, and then when you get the output, you're going to create the exponent of it and thus get the output. And so you can now here are the original data point, and here is how the model performs. For further resources on deep learning, of course, there is the chapter on deep learning methods here in Etienne's book. And well, that is the only resources that I wanted to share. There were questions about statistics and probability. It was beyond the scope of this study group, but of course we have brilliant courses on statistics and probability. There's this one by Dave Widoff, a senior Wolfram U instructor. It's an excellent course introducing you to statistics. And then there is also Introduction to Probability by Mark Vicuna, one of our newer instructors, but again does a great job of introducing probability. Very interesting course if you are, if that's what you want to look at. In the feedback, someone had shared that this is the data set you wanted to work with. I think that's a great choice to try machine learning. I was not able to go as far as trying to figure out what sort of machine learning I might be interested in using. I really ended up doing some very basic exploratory analysis. But there is this post by one of our Wolfram developers from a while back, but I thought this might be of interest to you, where he creates a tracker to analyze gas mileage. Different approach, different problem, but works with similar kind of data. I thought that might be interesting for you, and I will share this again, as I said, in this notebook, the review notebook. So what I did here is I imported the Excel sheets that were available on this site, and this is what the data looked like. So okay, you can see there are all these different sheets here. I just picked out the last sheet, and if you're curious about, how do you figure out, how do you work with different types of formats of files, you can look it up in the documentation. I would just go ahead and type in XLS, and then we have dedicated pages about each import export format you're interested in. An Excel page, you have details about the kind of elements you could import from a sheet, which row, which column, and lots of other options you could use to skip header lines or specify which is the header line. So I have all these sheets here. So I imported the data from the sheet called data 7, and looking at the Excel sheet, I saw the data really existed from the 4th row onwards, and I wanted columns 1 through 7, so I imported that data here in crude oil data, and I looked at the length of the data. So I had 2000 some rows, and for a very basic exploratory analysis, I used a dateless plot to plot the price of the crude oil against the date. So something very basic, has nothing to do really with machine learning, but this will probably be something that many of you will encounter as you start working with the data set. So I thought hopefully you would find it useful if I showed you a simple example of importing the data in. There was also a question about somebody wanting to work with images, but you have really large images, and so you wanted an option to work with the images, I believe, out of core. So data bin wouldn't be an option that I would recommend. Data bin is really for simpler data sets, small data sets. So don't go in that direction. You can have a data server, and then you can have Wolfram pull in the images. In fact, we have this example exactly showing out of core image classification with Wolfram networks, where instead of importing the image itself, you keep each image as a file object, and then you work with the file objects. The network knows that, okay, this is a file object, so I actually need to go and pull in the image before I can analyze it. So that would be a way to go to work with out of core images. All right, so good time to switch over to the other notebook I've prepared to quickly go through some of the stuff in how it works, not going through too much details here. Someone shared on the community thread as well, all models are wrong, but some are useful. A great way to start machine learning, really. Don't get too attached to your model. It's probably wrong. However, the difference that machine learning brings to the table with traditional modeling approaches is you start out with an idea of the model and you kind of develop the model by hand. However, in machine learning, you're starting out with a more open-minded approach. You let the model be created depending on the data. Now, does that mean you just like pull a model out of thin air? Well, that's not quite true either. You kind of start with a model family. So the training process is really a search process where you have this model family in mind, and then given the data, the computer is actually searching through a class of possible models and finds the one that's best among this data. The reason machine learning is so popular because we have the computer performing this search, which can do it really, really quickly. It can compute the model's performance really, really quickly against the test data, and then it can make the comparisons really quickly, repetitively, on tons and tons of data. So that's where machine learning makes things so much easier. Now, we saw a couple of different ways you could measure the model's performance, especially if you're using predict or classify. And every time the model, when you use the automated machine learning framework in Wolfram Language and you have classify running and the training progress indicator flashing, this is what is happening. It's trying a model on a subset of the data, it's measuring its performance, and then it's moving on to the next model, whether to check it can find something that performs better, or it has found something that is already doing great. So it tries to search efficiently through this model space, parameter space, like an optimization. And you do need, as I mentioned, a class of models to start with, often called a model family. And then finding good classes of models is really the main focus of machine learning research right now. I wanted to mention the example of transformers, right? Neural networks have been around for a long time. Deep learning has been around for a while, and there were all these different neural net models that were being tried on, and then suddenly this group of researchers come up with a transformer model that seems to be doing great on text data, and then before you know it, all sorts of these large language models available right now are basically using this model family, transformers. And so having an idea of that good model family is really important. Etienne in this chapter talks about non-parametric and parametric methods. So I just wanted to briefly talk about that. I kind of like non-parametric methods. They are very much, or they are much closer to the data itself, because the model really is the collection of the data. Your decision is all based on the data samples. For example, in nearest neighbors, you try to make a prediction based on the nearest neighbor you have in feature space to your data sample. Oh, if it looks like a duck, walks like a duck, quacks like a duck, it's a duck. So that's the similarity based model, neighbor based model, or memory based model. So you're not trying to parameterize your data, but in parametric methods, you build a model with a fixed set of parameters, example, linear regression, logistic regression, neural networks, some approaches that have been existing in statistics for quite some time. And then you learn the parameters, values of the parameters, by minimizing the cost function on the training data set. There was a question earlier on, I quickly noted in the question pane, about the difference between parameters and hyperparameters. So parameters is something that you find by training your model on the data. You adjust those parameter values as you build the model by showing the model every sample. Hyperparameter are values that need to be set for your model before you even begin the training process. And then do you end up changing hyperparameter? Yes, you do that, and you search through the hyperparameter space. And for this, you need something that's called a validation procedure. So we talked about test data set and training data set. You train your data on the training set, and you set aside the test set to evaluate the performance of your model. But in between, you have the validation set, which is kind of a test set you create for yourself, maybe from the training set. You set aside a little bit, you train your model on a subset of the data, and you test it on that validation set. And this allows you to select good hyperparameters. If your model is performing great on that validation set, you don't tune it. If your model is not doing great, you change the hyperparameter and then again run the process to see if the model performs better. The actual test set is always kept aside right till the very end of your project. After you're done all the validation, after you're done all the parameter tuning, hyperparameter tuning, then at the end of it, when you're happy with your model, you test it on the test set and you let the world know how well it performed on the test set. To get a good model, it's useful to have a nice big training set, test set, validation set. In the real world, often you don't have the luxury, so then you have to look out for ways to augment your data set. You can undersample it, or like you can undersample the more prevalent classes in your supervised learning set. You can upsample the rare class examples in your training set. You can do k-fold cross validation. You can do things like leave one out, where you train the model on everything but one sample, and then you test it on that sample, kind of use that as your validation set, just that your validation set has only one sample. So there are these tips and tricks you can use to, see how well your model is doing. Feature engineering, feature extraction, feature selection can always be very important. But then again, in this day and age of neural networks, it just seems like throw the entire data set at the model and it will figure out what is important. It'll figure out which feature is really important. What Wolfram Language, the automated machine learning framework of Wolfram Language, really helps us with is data pre-processing. You just throw the data at the functions and automatically it does data pre-processing, whether you have textual data, images, audio, video. So you don't have to spend a lot of time trying to extract information from the raw data. It does all this, the method selection, searching through the model space, searching through the hyperparameter space, tuning the parameters, using well-established, efficiently implemented algorithms to find the parameter values. It does all of that automatically for you. And so that would be one reason why you would use an automated framework like this, especially when you're just getting into machine learning. I'll end with this nice example I had that kind of showcases this, how easily this can be done with the Wolfram language. I have a synthetic data set of points and their labels. You can see the labels are just color swatches. It's a made up data set, so some of the points have red as a label, green and blue as the label, and you can see they're pairs of numbers, so lends the data set nicely to 2D visualization, which I'll show you in a bit. But first I'll build a classifier model and show you some information here. It decides to use the naive Bayes classifier here, but I could also change the classifier method, and I've shown this to you before. So I could use the method as decision tree. Again, both for classify and predict, I will encourage you to look at the documentation to see what are the well-established methods that are available. So these are the methods available for classify. And then I can have something like this if you're interested. Again, I'm going to share this notebook as well, so you can look at the code. Basically, I have a classifier model for each of those methods: nearest neighbors, logistic regression, support vector machine, random forest, naive Bayes neural network. And then you can see this is what the data looks like. And then for all other points in that feature space, this is how nearest neighbor will classify those points. This is how logistic regression will classify those points. This is how support vector machine will classify new example points, random forest, naive Bayes. That's interesting here, right? That little bit of blue, and then neural networks again. All right, so that is what I had for you to wrap up the series, to wrap up this session. We'll be sharing both these notebooks, the Q&A digest, as many of you have requested. Hopefully, you found the study group useful and you will be spending more time with the book. And we're always interested in hearing about your experience, so definitely fill out the survey at the end of the series. I think it has a couple more questions than your usual end of the day survey, so do take out some time to fill that out. Thank you, Luke, for answering all those questions. I see one last question I could probably answer right away. The image classification problem. Questions about getting the notebook. Yes, we will share the notebook. That's pretty much it for today. We hope to see you again at a future Wolfram U study group. Thank you so much for joining us.